Okay, in last class we have discussed bilinear transformation and we have find out the relationship between Z and S, and we have also find out that bilinear transformation is a stable transformation. In this class we will continue that particular session with relationship between analog and digital frequencies. Our topic is relationship between analog and digital frequency. We know from the last lecture that S is equal to 2 by T 1 minus Z inverse over 1 plus Z inverse, and we will find out the frequency relationship between S and Z by substituting S is equal to J omega. Actually it is sigma plus J omega, but we have substituted sigma is equal to 0 because we want to evaluate this particular side at imaginary axis only, and Z is equal to e to the power j omega, where r is equal to 1. Substituting the values, we will get j omega will be equal to 2 by t 1 minus exponential minus j omega over 1 plus exponential minus j omega. Taking exponential minus j omega by 2 common, we will get exponential minus j omega by 2 multiplied with exponential j omega by 2 minus exponential minus j omega by 2 at the numerator side, and similar manner we can do for denominator. So then this exponential minus j omega by 2 and exponential minus j omega by 2 will be cancelled out. We can see exponential j omega by 2 minus exponential minus j omega by 2 can be evaluated as sine function. Similarly, exponential j omega by 2 plus exponential minus j omega by 2 can be evaluated as cosine function. So we will do the necessary substitution and we will get j omega equal to 2j by t sine omega by 2 divided by cos omega by 2. J and this j will be cancelled out. So we will get omega equals to 2 by t tan omega by. This relation is for analog frequency. We can similarly find out omega will be equal to 2 tan inverse omega t by 2. The relationship we have obtained for analog frequency and digital frequency is a non-linear relationship between omega and this omega, as at analog omega equals to 0, digital omega will be equal to 0. We can see from this relation. As analog omega will be equal to infinity, this omega will be equal to pi. Now this non-linearity will allow one-to-one mapping between analog frequency and digital frequency. This one-to-one mapping that non-linearly compress the frequency is also called wrapping the analog frequency range. So analog frequency varies from minus infinity omega to infinity. So for minus infinity, digital frequency will be minus pi omega. For infinity, the value of omega will be pi. So the digital frequency ranges from minus pi to pi are mapped completely with minus infinity to infinity in the analog frequency range. So this particular compression of frequencies to map minus infinity with minus pi and infinity with pi called wrapping effect or frequency wrapping. This non-linearity between analog frequency and digital frequency, this behavior avoids the effect of aliasing, which is predominant in impulse invariant technique at the expense of compressing or wrapping the analog frequency. Now this compression will have some side effects which can be seen by this graph, which is plotted between digital omega with analog omega. So the relation is omega is equal to 2 tan inverse omega t by 2. When this omega goes to infinity, this omega goes to pi. We have provided of uniform frequency samples in analog domain and see its response in digital domain. We can see the compression is more dominant in higher frequency regions compared to lower frequency regions. So we can say higher wrapping is performed at higher frequency. With increasing frequency, the effect of wrapping is more evident. Now we see this wrapping effect is very important in bilinear transformation. So we will discuss more details about this wrapping effect in phase and magnitude response. So the effect of wrapping on magnitude and phase response. The magnitude response can be seen as the relation between omega and this omega. This is for the digital and this one for the analog. We can see this omega p lies linearly with this omega p, so there is no wrapping in the magnitude of the passband. There is no wrapping effect in the passband, but the stop band sees the wrapping effect. Frequency are compressed in the stop band, whereas the frequency in the analog domain goes like this in stop band, and they are compressed in digital domain. The magnitude response can be concluded as for low frequencies, wrapping effect is linear and so the passband is hardly distorted. For higher frequencies, the mapping is non-linear and hence stop band ripples are distorted. Next, we will see the phase response. We have provided a linear phase in analog domain, which comes out to be non-linear in digital domain. That's mean the phase part is distorted. Now we know linear phase becomes non-linear after transformation. Now we can conclude 2 points from this magnitude and phase response are: magnitude is preserved only if the specifications require piecewise constant magnitude. What does it mean? It means if we doesn't bother about the ripples in the passband and stop band, then magnitude is preserved. But if we bother about the ripples, then magnitude is not preserved in this transformation. Second point is phase response of analog filter is not preserved after transformation. It transforms from linear to non-linear, as we have seen with the phase response. Now after these two problems, what we can do to remove this aspect, which is called pre-wrapping. This method is used to compensate for the non-linear relation between the frequencies or the wrapping effect. For this method, pre-wrap the specifications for the designing of digital filter, which goes as, now for designing a digital filter, specifications are generally given in digital frequencies. So to apply this pre-wrap specifications, we'll first convert specified frequencies into analog frequency using the transformation method we have determined earlier, that is omega is equal to 2 by t tan omega by 2. This process is called pre-wrapping, and this process will overcome the adverse effect of wrapping effect. First, we will find out an analog filter using the given frequency, that is Hs, and then we will transform that Hs to Hz using bilinear transformation. So after this, wrapping and pre-wrapping effect, we will go through some advantages and disadvantages of bilinear transformation. So the first advantage is bilinear transformation is stable and provide one-to-one mapping method between analog omega and digital omega. And the disadvantage is the relationship between analog omega and digital omega is non-linear in nature. Another advantage of bilinear transformation is there is no aliasing effect in bilinear transformation. And second disadvantage of bilinear transformation is that if we have a linear phase analog filter, then we cannot transform the same filter into a linear phase digital filter, because there is a non-linear relationship between analog omega and digital omega. As compared to previous IIR filter design techniques like approximation of derivatives and impulse invariant technique, bilinear transformation provides no limitation of filter types. That's mean we can apply bilinear transformation for designing any kind of filter, maybe high pass, low pass and band pass or band stop filter. Bilinear transformation also preserves the magnitude response of an analog filter with piecewise constant magnitude. It does compresses the ripples, but if we go for the piecewise constant magnitude, then BLT preserves the magnitude from analog filter. Next is the wrapping effect can be removed by using pre-wrapping of analog filter, and with this advantages and disadvantages, we have completed the bilinear transformation. That's all for this lecture. Thank you.